In this lesson, we are going to work with primary trigonometric ratios. They're actually very important when it comes to working with right triangles, but in order to understand primary trigonometric ratios, we need to be very comfortable with similar triangles. So I think we've spent quite a bit of time on similar triangles. We talked about how to prove two triangles are similar to one another. We talked about how corresponding sides of similar triangles are proportional. We talked about the relationship between the areas of similar triangles. So with all that strong foundation with respect to similar triangles, I really think we are ready to talk about primary trig ratios. Now, before we talk about primary trig ratios, let's just look at this beautiful right triangle here, and we need to name the sides of a right triangle. Okay, so one of the sides of the right triangle you should already know the name of, which is the longest side. Okay, we should all know the name of the longest side of a right triangle, and that is the hypotenuse. Now, the other two sides of the right triangle, you might not know the names of these ones, but the names depend on where the given acute angle is located. Okay, so a right triangle obviously has a right angle, but it has two acute angles. So in this case, we're given angle R. Okay, so relative to angle R, PQ has a name. Okay, PQ is called the opposite side, because if you look at it, it's opposite to the given acute angle. Okay, it's opposite to angle R. Now, the last side of the right triangle is called adjacent. Okay, if this is angle R, the side is adjacent. QR is adjacent beside angle R. So the side that's not the hypotenuse, that's the adjacent side. So we have hypotenuse, which is something we're very familiar with. We have the opposite side, the side which is opposite to the given angle. And then lastly, we have the adjacent side, which is beside the given acute angle, which is not the hypotenuse. Okay, so let's just fill in these blanks very quickly. The blank side is directly opposite from the given acute angle. Okay, so the opposite side is directly opposite from the given acute angle. The blank side is the side that forms the acute angle and is not the hypotenuse. That's the adjacent side. The adjacent side is a side that forms the acute angle. And lastly, the hypotenuse is always the longest side of the right triangle. And of course, we also want to add the fact that the hypotenuse is directly opposite to the right angle. So that's how you know that's the hypotenuse. Now, be careful, okay? The opposite side and adjacent side, it really depends on the acute angle that we're given. If we were given angle P instead of angle R, guess what? If you're given angle P, PQ is no longer the opposite side. PQ is now the adjacent side. And if you're given angle P, QR becomes the opposite side. Okay, so we're going to get lots of practice labeling the triangle, but I just wanted to mention that very briefly. So whenever you get a right triangle in the beginning, when you're still practicing, I would highly recommend you to label the sides of the right triangle. Okay, so it's opposite, adjacent, and hypotenuse. All right, so now we're one step closer to developing the trig ratios. So before we do that, let's look at this diagram here. So I see quite a few triangles here. I see triangle ADE, the smallest one. I see triangle AFG. I see a triangle AHI, and I see triangle ABC. Okay, what is the relationship between those four triangles? Hopefully, you'll see that they are similar. Those four triangles are similar. how do I know that? Well, they all have angle A in common, and they're all right angle triangles. So based on the fact that angle similarity, then those four triangles are similar to one another. Okay, now let's take a look at the following ratios here. So they say DE over AE. Okay, DE over AE. So we have DE here and AE here. And then we have FG and AG. Okay, so let's use our different colored pens here to help us out. So DE, AE. So we're looking at those two sides. And then let me just grab a different color here. And then we have FG, which is this side, over AG. Okay. So, because triangle ADE is similar to triangle AFG, what can we say about those two ratios? DE over AE and FG over AG. What can we say about those ratios? Well, hopefully we can agree that the ratios are equal. Yes, FG is longer than DE. Yes, AG is longer than AE, but because the corresponding sides are proportional, then the ratio is still the same, right? So I don't know, let's make up some numbers. Let's say this is 1, DE is 1, and let's say AE is 2. Okay, so if you double the lengths, and then FG would be 2 and AG would be 4. So you have a ratio of 1 over 2 and 2 over 4. And they're the same, right? They're equal. And you can make the same argument. So you can do HI, okay, for the third ratio, HI over AI. And this could be, let's say this is 3, and this would be 6. AI would be 6, okay? 1 over 2, 2 over 4, 3 over 6, they are equal. All right? And lastly, you could do BC over AC. Yes, the lengths are much longer, but the ratios are the same. Okay? So we're not looking at the individual lengths of the sides of the triangle. We're looking at the ratios. Okay? So if that's the case, they're equal. Okay? The four ratios are equal. You could do the exact same thing. Okay? Take your time. Compare the ratios of AD over AE to AF over AG. Okay? And you'll hopefully see that they are equal. And they're only equal because of the fact that we stated above. Because of the fact that the four triangles are similar to one another. Okay? Yes, AF is longer than AD and AG is longer than AE, but they're similar triangles, so the ratio will be the same. They'll be equal. So equal and equal. So take your time, study the ratios and highlight the diagram, and you'll notice that, yeah, the ratios are equal. All right. So what we really want to do is actually work with these ratios. So there are actually names to the ratios that we investigated, that we were working with just now. Don't forget, the following ratios are only for right triangles, okay? If you don't have a right triangle, please don't do this, okay? You can't talk about, you can't talk about these ratios. You can only talk about like the sine ratio and the cosine ratio when you're working with the right triangle. Okay, so sine, the ratio of the side, okay, this one, we have to know the definition, so I'll just give you this one. The ratio of the side opposite a given angle to the hypotenuse. cosine is the ratio of the adjacent side of a given angle. Well, it's the acute angle, but anyways, adjacent a given angle to the hypotenuse. And lastly, the tangent ratio of side opposite a given angle to the side adjacent the same given angle. Okay, so we have short form sine is sin, the abbreviation for cosine is cos, so sometimes we just say cos, and for tangent we just say tan. One last time, if I don't have a right triangle, please don't talk about opposite over hypotenuse or adjacent over hypotenuse, because you don't label acute triangles with the words opposite and hypotenuse. You only label the sides like that if you have a right triangle. Okay, but don't worry, we will work with non-right triangles in the next chapter. In this chapter, we're focusing on right triangles. Okay, so sine, cosine, and tangent are all ratios of two sides for any given right angle triangle. Given an acute angle on a right triangle, we can determine any of these ratios. So we have a little shortcut, or an acronym, sorry, to help us remember the definition of sine, cosine, and tangent. So we have SOHCAHTOA. So we write SO as an SOH because sine is defined as a ratio of opposite over hypotenuse. Okay, so this basically reminds you that sine is defined as opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. It tells us what the definition of the ratio is, just in case you forgot. Okay, so let's use our calculators and find what sine 30, cosine 20, and tan 45 is. So sine 30, if you punch in your calculator, is half, or 0.5. That's what the calculator is telling you. So be careful. It's not telling you the length of any of the sides of your right triangle. I have no clue what the side lengths are. But what sine 30 degrees is telling me is that the opposite side, the opposite side to the hypotenuse is 1 to 2. In other words, the hypotenuse is twice as long as the opposite side. I don't know how long the hypotenuse is exactly, but it's twice as long as the opposite side. Well, what about cos 20? Well, this one I need my calculator. Cos 20, 0.93. Let's see, 1 second. 3 decimal places. 0.94 actually, 940. Okay, so once again, I don't know any lengths of this triangle. All I know is the ratio of the adjacent side to the hypotenuse. Though the lengths of those two sides are actually very, very close because it's a ratio of 0.94. Okay, what about tan 45? Now, before I spoil tan 45, I'm going to draw a right triangle. Now, if this angle here is 45 degrees, then this angle here must also be 45 degrees, right? Because they total to 180 degrees. And oh, this is an isosceles triangle, right? Okay. So remember, tan, TOA, tan is defined as opposite over adjacent. So let's say if we're looking at this angle here, this 45 degree angle, then this is the opposite side, this is the adjacent side, and this is the hypotenuse. So what's the ratio of the opposite to the adjacent side when we're looking at that 45 degree angle? Well, the ratio is 1. I don't know the lengths of the opposite and adjacent side, but what I do know is the ratio is 1 because they're the same length. It's a right isosceles triangle. So let's check, okay? That's what the triangle tells me. Oh, yes. So tan 45 degrees, 1. Beautiful. So the calculator is so powerful. If you give the calculator the angle, the acute angle in the right triangle, it spits out the ratio. And you know what? If you give the calculator the ratio, it spits out the angle. It gives us the angle. So what you have to do is take inverse sine of 0.75. So if the ratio of the opposite to hypotenuse is 3/4, what's that acute angle? They say round it to the nearest degree. So let's try it first. Inverse sine of 0.75. Bam. 49 degrees about. Okay. What about beta here? Inverse cosine of 3/5. So if the ratio of the adjacent side to the hypotenuse side is 3/5, the angle is about 53 degrees. And lastly, if the ratio of the opposite to adjacent side is equal to 1, then what's the angle? The angle is, we already know. We don't need the calculator. Well, what did we say earlier? When the ratio is 1, the angle is 45, right? So you know what? Let's just double check with our calculator. Inverse tan of 1, boom, 45 degrees. Beautiful. Okay, so the calculator is so nice. If you give it the angle, it gives you the ratio. If you give it the ratio, it'll give you the angle. Okay, let's work on example 3a here. Calculate the measure of the angle when sine theta equals 3/2. So we're given the ratio. The calculator should be able to spit out the angle. So inverse sine of 3/2. Ooh, math error. So what does that mean? The calculator is actually saying to us, no possible angle of theta will give us a sine ratio of 3/2. So why is it not possible to give us a sine ratio of 3/2? Let's think about it. Okay, sine is defined as the ratio of the opposite side to the hypotenuse. If you have a ratio of 3/2, that actually means that your opposite side is longer than that of your hypotenuse. Well, how does that make any sense? No wonder it's not possible for any angle of theta to give me a ratio of 3/2, because the opposite side must be shorter than that of the hypotenuse, not longer. So in fact, the ratio of the opposite side to the hypotenuse cannot exceed 1, okay? Because the hypotenuse side must be longer than that of the hypotenuse. So, the hypotenuse must be longer than that of the opposite side. So in fact, if you did like any inverse sine of, I don't know, let's say even 4/3, that would also be error because your opposite side is longer. If you did inverse cos of 5/3, same thing. The hypotenuse has to be longer than your adjacent side. Okay? All right, so you know what? Let's put these trig ratios to good use. Let's use the trig ratios to help us solve for missing side lengths of right triangles. So I didn't do the markings, but these are all right triangles, okay? I think something got deleted. Anyways, let's do the question. So I'm trying to solve for the missing side. So I'm going to do the labels here. So that will allow me to pick the right trig ratio, okay? Should I use sine? Should I use cosine? Should I use tangent? Well, I'm trying to solve for the opposite side and I have the hypotenuse. So which trig ratio involves the opposite side and the hypotenuse? And the answer is the sine ratio. Okay, so sine is our friend. So sine 33 degrees is equal to x, or 8.34. This is very powerful. Okay, this is very powerful because this is saying that sine 33 degrees, the calculator will spit out what the ratio is. Okay, if the acute angle is 33 degrees, the ratio of the opposite to the hypotenuse side, you know what, let's check it out, is approximately, let's say 0.54. Okay, if that must be the ratio based on what the calculator said, if that is the ratio between the opposite to the hypotenuse, the opposite side of the hypotenuse, and I also know that the hypotenuse is 8.34 units, then I know what x must be. I can solve for x because x over 8.34 must be equivalent to this ratio spit out by the calculator, which is about 0.54, okay, because the triangles are similar. Okay, so that's what we were trying to get at on the first page. Because the triangles are similar, then these two must be equal. Sine 33 degrees must be equal to x over 8.34. And if that's the case, we can use our basic algebra to solve for x. Multiply both sides by 8.34 and we're done. But it's all about linking what we're doing here with your knowledge of similar triangles. So 8.34 times sine 33. So we're going to round that to 2 decimal places, 4.54 about. Okay. So here, opposite, adjacent, hypotenuse. So I'm trying to solve for the hypotenuse. I have the adjacent side. So in this case, cosine is our friend. Okay. Cosine of 58 degrees, whatever that ratio is, the calculus is going to help me. I don't know what the ratio is. The calculus is going to help me. That ratio has to be equal to 4 over x, based on the fact that the triangles are similar. And if I know that, then I can solve for x by using my my algebraic techniques. So I'm going to multiply both sides by x. Okay. And then divide both sides by cosine of 58 degrees. So x is 4 over cosine of 58 degrees. So we're looking at about 7.55. And that's pretty good because hypotenuse is the longest side. This is 4, 7.55. Seems reasonable. Seems reasonable. Okay. Let's take a look here. Label the sides, opposite, hypotenuse. So I'm not going to label the side because I know what two sides are involved. O and H, SOHCAHTOA. So sine, hopefully you can agree with that. So sine 40 degrees, whatever that ratio is, the calculator is going to tell me, must be equal to 5.3 over x. If that is the case, okay, and it is because it's based on our knowledge of similar triangles, then I can solve for x. I'm not going to skip this step. So we're looking at about 8.25 approximately. All right, just be careful. Make sure you're using the right trig ratio, okay? There's a huge difference between sine and cosine and tan. The definitions are totally different, as you know from earlier. Okay, this one, I'm looking at adjacent and hypotenuse. So cosine is the one to use. We're looking about 6.97. Yep, looking good because it's longer than 4 and it has to be because it's the hypotenuse. All right, let's solve for these two triangles, label the sides. It's really going to help us pick the right trig ratio. You do not want the wrong trig ratio. That would be catastrophic. This one is tan. All right, we're looking at about 4.55. So what about this one? We're looking at opposite, adjacent. So tan it is. All right, let's see what 4, 10, 55 degrees is. 5.71 about. So in example 4, we've been solving for missing side lengths, but the calculator is actually very powerful. If you give the calculator a ratio of two sides of a right triangle, it can actually give you one of the acute angles. So that's what we're going to do now. So yes, you can solve for missing side lengths, but you can also solve for missing angles. Now remember, we're working with right triangles here, okay? Right triangles. Okay, so just like before, I'm going to label the sides. Well, don't do that. All right, so what are the two sides involved here? We're given the opposite and the hypotenuse side. Sorry, the opposite side and the hypotenuse. So I'm thinking we know the sine ratio. We know that the sine ratio is 5 over 7.8. So if you tell the calculator that the ratio, the sine ratio is 5 to 7.8, we can actually solve for this acute angle right here. Okay? So theta is the inverse sine of 5 over 7.8. So give the calculator the sine ratio, and he will tell you the angle and nearest degree, so we'll look about 40 degrees. Okay? So this one is adjacent and hypotenuse. So I have the cosine ratio. All right, if the cosine ratio is 4 over 7, let's ask the calculator, then what must the angle be? What must be the acute angle? 55 degrees approximately. Over here we have hypotenuse, adjacent, opposite. So which ratio do we have? We have the adjacent, sorry, the cosine ratio. Cosine of theta is 5.2 over 6. And if that's the case, I can use the calculator to determine the acute angle. So we're looking at about 30 degrees. And this one, you know what? I'm not going to use my calculator. It's the right isosceles triangle. I know the angle must be 45 degrees. But you know what? Let's say I forgot about that. I'm working with opposite and adjacent. So this time I'm going to tell the calculator I have a tan ratio of 5 over 5. Inverse tan of 5 over 5. What is the angle, Mr. Calculator? And it's not approximate, it's perfect. What is the angle, Mr. Calculator? 45 degrees, like I expected. Okay, so basically in this handout, there was a lot going on. We first used similar triangles to build up the relationship of sine and cosine and tan. And then using the sine and cosine and tan ratio, I can solve for missing sides of a right triangle, or I can solve for one of the acute angles of the right triangle. Very powerful stuff.